We saw the integral test, which I'll remind you of. It says if you have a positive decreasing function, and when you plug in values of n, you get terms in a series, then that infinite series and the integral either both converge or they both diverge. They do the same exact thing. So let's do an example. Does this infinite sum converge? Are these terms adding up to a finite number or not? So I'm going to define my function f of x to be 1 over x log x. This function's positive. If you stick in numbers bigger than 2, the bottom is positive and therefore the whole term is positive. And additionally, this function's decreasing. You could double check that if you take the derivative and show that the derivative is negative, meaning the function's going down. But I'll just observe that the bigger values of x I plug in, the smaller this number gets. So I'm going to intuitively just see that the function's decreasing. So deciding if this converges is the same as deciding if the integral converges. So I'm going to do the calculation. The integral from 2 to infinity of 1 over x log x. My first step every time I see an improper integral with an infinity sign up here is to take a limit. So I write it as the limit as t goes to infinity, the integral from 2 to t of 1 over x log x dx. Evaluating this integral, I will do a u substitution. So I'm going to let u equal log x. Then, taking the derivative on both sides, du is 1 over x dx. So I'll use my u substitution and get the limit as t goes to infinity. Whenever you do a u substitution, you should change the limits of integration. So if x is equal to 2, u should equal log of 2. So the integral goes from log 2 to log t. 1 over x dx becomes my du. 1 over log u becomes 1 over u. So I put in my u substitution. Now I can integrate. So this would be the limit as t goes to infinity of log u evaluated at log 2 and log t. So this is the limit as t goes to infinity of log of t minus log of 2. Now, this thing has limit infinity. Log of t has limit infinity as t gets larger. So log of t also has that same property. This is infinity. So they both diverge. So the series n going from 2 on of 1 over n log 2 or log n diverges. I'd like to do another example, a pretty important example of the integral test. So here's the question. For which values of p does the sum going from 1 on of 1 over n to the p converge? This is known as a p series because somebody decided that they should put p as this exponent. So we call it as a shorthand p series. Okay, so here's my answer. I'm going to use the integral test. I'm going to look at the integral from 1 to infinity of 1 over x to the p power. So this is my function, 1 over x to the p power. You could check that it's always positive, and if p is non-negative, if p is bigger than or equal to 0, then the function's decreasing and it has the desired property. So this will be my function f of x in the integral test. So I evaluate the integral, I get the limit as t goes to infinity, integral from 1 to t. Now, I'm going to rewrite this as x to the negative p dx, and when I integrate, I get x to the negative p plus 1 power divided by negative p plus 1. Because when you integrate a power of x, you add 1 in the exponents and divide. This will be evaluated at 1 and t. Now this is not true if p happens to equal 1. So if p equals 1, then the integral is not this form, it's actually logarithm. You could see that this formula doesn't make sense because if p happens to be 1, I'm dividing by 0, which is nonsense. So I'm going to consider the case when p is not equal to 1. If p is equal to 1, we've actually already done the problem. If p is equal to 1, I have the sum of 1 over n, which is the harmonic series. I know that diverges. So I'm going to assume that p is not equal to 1. So I have the limit as t goes to infinity. Plugging in t, I get t to the negative p plus 1 power over negative p plus 1. And then I subtract and I plug in 1. So that's what I find. Now pay attention to this next step because it's a little tricky for some people. In my experience teaching this course, I know that some students get a little tripped up, so watch out for what I'm about to do. I want this limit to actually be a finite number. I want this limit to actually be a number so that the sum will converge. That means, since I'm taking the limit as t goes to infinity, I want this circled term, I want this term here to not have limit infinity. I want this term to have limit 0. I want this term to not be there, so I get a finite number. I'm taking the limit of powers of t. I need the exponent, I need the exponent here, which is negative p plus 1, to be negative. If the exponent is negative, then powers of t get smaller and have limit 0. If the exponent here is positive, like for example, if p was negative 3, the exponent would be t to the 4th power. That would have limit infinity. I don't want that. I actually need the exponent to be negative so that I'm really getting smaller and smaller terms. So I need negative p plus 1 to be negative in order to get this term to have limit 0. This says that p has to be, well, you can add p on both sides. Maybe I should write it this way. This says 1 has to be less than or equal to p. So again, the logic, I need this exponent to actually be negative so that the limit goes to 0. If this exponent was positive, the limit would be infinity. I get like t to a positive power that has limit infinity. So that means I need that exponent to be negative, and I wrote down an equivalent condition. So what's the conclusion? Conclusion. This sum, n going from 1 to infinity, of 1 over n to the p power, converges when p is bigger than 1. It diverges if p is less than or equal to 1. So as one brief example, the sum n going from 1 to infinity of 1 over n cubed converges because the power p here is 3. Okay, wonderful.